Okay, so what we've done so far is concurrency control and transactions. We've gone and looked at the general issue of concurrency control and said that to understand this, we need to understand transactions. And then we looked at simple locking, just one lock. That's all you have to implement. And it's distributed implementation. Okay. So we've done this. And what's left? Multiple locks. Right? Maybe they raise some issues that single locks don't raise. Okay. Maybe multiple lock types. Okay. We'll see why we might need those. Alternatives to locking. Okay, I talked about optimistic locking, and I said that's an oxymoron, because when you're really optimistic, you don't do locking. Okay, so when you don't do locking, what exactly do you do? Okay, so that's optimistic transactions. Also programmer-defined locks. Okay, that's interesting. As a programming language person, what if you define a new ADT? Do you have to change your transaction implementation, or can you use the existing transaction implementation? And if you use the existing transaction implementation, what are the costs of doing so? Okay, so we're going to look at that. There's some work that's been done for queues that I'll be looking into. And I kept talking about nested transaction. I kept saying, we're not going to consider them. But twice or thrice I mentioned them here, which means they're relevant to what we're talking about. Okay, so I added some nested transaction slides yesterday also. Okay, so that's the plan. And hopefully between today and next Monday, we'll be able to finish concurrency. Okay, and this is really important stuff. I mean, when you think of cloud computing, it's all kinds of concurrency issues are going to arise there, and that's considered a hot area. Okay, that's what a lot of companies are betting on. I don't know how they'll make money out of it, but maybe they'll find a way. Okay, that's what they're saying, right? They're saying that Microsoft is going to now, bet on cloud computing, and yet we get OneDrive for free, and we get Dropbox for free, and we get Google Drive for free, and Amazon Drive for free, and I have all these drives here, and they all have quotas, but if you add these quotas up, that's a lot of space. So I don't, hopefully they will make money, okay, but this is an interesting area. Okay, we saw how single locks worked. Okay, the whole idea was that we're going to try and prevent these cycles. Okay, these cycles cause non-serializable transactions. So what we want to do is delay actions through locks, so that what was, where there was a cycle, now there is not. Okay, and we see that happening here. That what we are ensuring here is that the transaction 2's operations occur after transaction 1's operations. Okay, we really want the write of the transaction 2 to happen after the read of transaction 1, and since the read of transaction 2 follows the write of transaction 2, that also has to happen. Okay, so that happens because this transaction locks the item, and it doesn't free it till it has done the read. Okay, so this transaction that tries to go and lock it must wait this whole period, and then it does this write. So we serialize things. Okay, works nicely. If these two operations were reversed, then the read operation could have happened earlier, right? Because then the direction is only one way. It could have read what this guy wrote. Okay, but since it happened in this direction, it had to wait the whole period. Let's go to multiple items now. Okay, transaction 1 reads item 1, writes item 1. Transaction 2 writes item 1. Then it writes item 2. Okay, and transaction 1 writes item 2. Okay. Now what's going to happen with locking? This is going to request a lock for item 1. Okay, and this transaction will have to wait for that to finish. Okay, and So it has to wait. So at some point it's going to release. So let's just follow. Okay. Locks this, writes it, waits, it frees it, right? It writes it. Then this guy goes and locks item 2. Okay. And this guy goes and follows. Things seem to have worked. Right? Acts as a serial. And I said they seem to have worked. Well, they have worked, but will they always work? I mean, it is, the writes are following this. That the dependencies are always this way. With locking, could things become messy where, yeah?
Are there situations where a user would want to have 2 locks at the same time?
Sure. A user could ask for multiple locks at the same time. So here, in fact, I freed the lock. This transaction was just being nice. It freed the lock. Okay, it could have gone and freed the lock after it got locked. Which do you think is better, by the way? Freeing immediately after using the resource, or taking your time about freeing? The way I said it, it seems the latter is bad, right? Just confusing you guys. The question is, does locking guarantee serializability? The way we, that semantics we've said. You got it. Before you do an operation on an item, you must lock it. At some point later, you free it. That's the semantics. Okay? You can't do the operation without asking for a lock. And just saying that, is that enough to go and ensure serializability? You're guessing no. Remember, explain all answers. So remember, this first subscript is which transaction is doing that. Okay? And this one is which item is being locked. Oh, this should be L1. I'm sorry. Good. And this should be L1 and F1. Yeah, so that's what it's saying, D2.
Yes, so D1 should have L1, right? And not transaction specific, like you said, it should be.
Okay, so firstly, all of these things should match. Okay, 2, 2, 2, 2, 2, 2. Okay, and my cutting and pasting caused problems. This should be 1, 1, 1, 1, 1, 1. Okay, here we are saying which item we are locking. Okay, before I write to D1, I must lock it. Right? Before transaction 2 writes to D1, it must lock it. And transaction 2 then locks D2 and frees D2. Okay, so this just these things. I mean, I could have used spatial. I needn't have said 2 or 1, but at one point I went and serialized these guys. So when I'm serializing them, I really need to indicate which was 1 and which was 2. If I'm going to put them in a serial order, that's the reason why I did it. Maybe it's confusing.
Also, like the height,
The type.
which we are showing, like we want W1, T1 to execute first, like in the left.
This is timeline.
Yeah.
Going down is timeline. So this action occurred first. That's why this guy waited. That's what's happening here, right? This guy did a write, then this guy did a write. So this guy, there's a dependency from here to here, and dependency from this to here to here.
But there is not in that. It's doing.
No.
Why is that doing W2 last, right? So in the timeline.
Yeah, this W?
No, the last the W2 T2 is performed last, right?
Yes.
After W1, like, but in the left picture it's showing something else.
Because this is what the transaction was. In this transaction, this guy wrote D1 first, then D2. Okay, again, this should be W1. I'm sorry. Okay, this should be W1. So in this one, and you know, this is going to propagate to all the slides because I think I copied a lot. So, but okay. So this is all ones, and he did D1. Then he thought about it, you know, computing, writing, doing some loop. Then it went and did D2, and this guy did D1 and D2.
I think he's saying that in our lock thing, T1 does the write on D2 before T2 does the write on D2.
Yeah, but that is not reflected in the
Oh.
lock timeline, right?
Yeah.
Okay, hang on. T1 does the operation on D1 before D2, right?
No, just D2. If you just look at D2,
Yeah.
T1 does the write on D2 before T2 does the write on D2 in the lock.
I'm just saying that the left picture and right picture doesn't seem to be.
They didn't. That's the whole point of locking.
They have different end results.
They have different end results. That's the whole point. We are trying to avoid this situation.
Oh,
Oh, because the one on the left
It's not serializable.
in consistent state.
So, yeah, it's not serializable. There's a dependency. That's what we did in the first lock thing also. That's the whole point of locking. Right? So when I said things seem to work well, I mean it happened late. That was not a bug, it was a feature.
Okay.
Okay? Yeah.
So let's say that that one user one is making a transaction that requires it to make edits to D1 and D2.
Yes.
So it acquires a lock on D1
Yes.
and then tries to acquire a lock on D2.
Good.
User 2 is also making an edit that requires it to the transaction requires it at D1 and D2.
Right.
So it gets a lock on D2.
D2 first.
D2 first.
Oh.
Then it requests a lock on D1.
Oh, what's going to happen?
It's deadlock.
Well, is deadlock bad or good?
Bad.
What's worse, deadlock or non-serializable transactions?
At least, so deadlock does prevent the error. At the expense of preventing everything else.
Depends on your definition.
What you know, you want to change make the whole world inconsistent and just, you know, some stupid program just blocked. That happens all the time. You know, we haven't changed anything fundamental. We haven't rewritten history in some strange way.
Yeah, I'd say breaking is better than producing inconsistent data.
And so, you know, deadlocks can be detected. There's a lot of algorithm for deadlock detection. So we detect deadlocks and we say, okay, you two guys are involved in deadlocks, I'll abort one of them. And now things go.
So that requires, instead of doing this like little like sub-right level lock, you really want to lock the whole transaction, right?
Well, we want D1 and we want multiple locks. Why do we want multiple locks other than one lock?
Then we're not serialized.
No, one lock will be serializable.
Well, but the whole transaction may not be.
One lock will guarantee. If I just say lock, then it's more conservative. Multiple locks means, because that one lock will capture both D1 and D2.
Okay.
Yeah, that's what I meant.
All right.
Okay, so we want multiple locks to have concurrency. So things would be bad if we won't have deadlocks and we have non-serializable transactions. Can that happen? Work again with your example. You were there. We access objects in different order. Actually, even in this example, I can create that problem. I just have to make the timing such. But with that example, it's easier to deal with. So let's go to that example. So here what's happening is T2 is performing an operation on each object after T1. It's very nicely done, you know, that it's succeeding. And the question is, what if it happens in the reverse order and it doesn't get caught? Things can happen in the reverse order. Okay, unless we tell every transaction that items are all ordered in this way, and please access resources in that order. You should never write D2 before D1. Okay, that's constraining. Okay, again, this should be W1. Okay, so we want to prevent this situation from happening, and this guy locks D1, then he writes to D1, right? This locks D2, and the first guy frees it. Can you see that causing a problem? So what's transaction 2 going to do now? It's going to free this, right? What's it going to do next? Lock D1? Is it going to be able to lock it? So this guy can lock D2. This guy can lock D1. No deadlock. Bad news, right? Because we have a dependency of this kind from here to here and from here to here. So how should we fix this?
Lock everything that you're going to use in the transaction.
Lock everything.
That you won't write in the transaction.
But we are locking everything we want to write, right?
Lock it at the beginning.
Lock at the beginning.
Before you start the whole transaction.
And free it.
At the end.
What if I just said free at the end? Would that be enough? The problem was that this guy got freed here. If it wasn't free till the end, this guy couldn't have got it, and it would have had a deadlock. Of course, in your situation, there'd be no deadlocks there. Well, there could still be deadlocks, because they could go and lock in different orders. Okay, but the deadlock would be caught a little earlier. So if we do all this stuff, freeing in the end, locking in the beginning, we are reducing concurrency. So how can we have a cake and eat it too? How can we have the maximum concurrency possible while not causing any problems? Locking at the end is a little too conservative. Locking in the beginning is not needed. Okay, we just realized we were being too conservative there. Yeah.
So, for example, if and this is a tangential what if, related, is what if user 1 writes to D1,
Yeah.
and then later on in its sequence of operations, the transaction reads the value of D1.
Yeah.
If we free D1 after we write to it before we read to it, another user is able to change that value, and then our transaction, they're not serializable.
Yeah, so we're having even more problems, right? The fact that we released it immediately, is bad, that's for sure. Okay, and you're telling me another problem that might occur because this transaction might need the value again later, okay? And in that case, we again run into trouble. So what I'm saying is that we want to free it not immediately, yet we don't want to free it at the end.
We can request the lock at the beginning for all the things we want to write.
That's what Patrick was saying.
And after I finish write off one of the items, we just release it.
But that's what I did. I did it here, and I got into trouble.
I mean, I can.
Oh, so you're saying request all of them in the beginning and release them incrementally.
Yeah.
That could work. Okay, I think it's a dual of the other situation. Okay, but we can do better. Let's begin. Let's assume that we're going to request. And the thing is, the problem with your approach is that you might not know what locks you need. There may be if statements in your transaction. Okay, so you know that you need a resource only when. Okay, and of course, the solution I'll give you also has the same problem, but it has to some smaller degree.
Change the order of the log, the second item, and free the first item. So you free the first log after you request get the second item's log.
Fantastic. So say it in more general way. You're saying request lock for the free the first lock after you got the second lock. Not get all the locks in the beginning. Get the locks incrementally, but don't free the first lock till you got the second lock. And can you generalize that too? If there are n items, that's easy, right? Going from 2 to n is easy. You don't free any item, free any lock till
You got the new log.
you've got, we have n items,
You got all the logs.
you got all n locks. That means the transactions will have a phase in which the locks grow and then a phase in which the locks shrink. That's called two-phase locking. We just invented two-phase locking. Okay. So this is what's happened, which is bad. Locks are freed too quickly. Okay. Get all locks before doing any operation. Early binding and keeps locks for longer than necessary. Okay. Two-phase locking. And same problem with releasing all locks at the end of transaction. Okay. A transaction is a growing phase when locks are added and not released. Okay. Then it is a shrinking phase when locks are released and not freed. Okay. So I talked earlier about two-phase commit. That's different. That's in a replicated system, and you have a consensus algorithm, and that's when you deal with the Byzantine general problem. This one is two-phase locking. Okay. So let's go and see non-two-phase and phase. So let's consider a situation where we access items in the same order. Okay, this is non-two-phase, even though it worked. Okay, it did work because things were interleaved, because this guy was freed before this guy was acquired. Okay, this free request occurred before the last lock request. Okay, but it worked. We were going to do it in two-phase locking. You would lock the item, you would write the item, and at this point, the next operation would be, okay, this guy would locking item 2. Okay. Okay. So the previous one worked too. This one is going to have less concurrency, but there are more guarantees right now. Okay. So growing phase, shrinking phase. Sorry, I got this wrong. Okay, I should have these reversed. Okay, I got a lot. I should now have another free here. Okay, I just added this before class, and of course you make mistakes.
So,
Yeah.
if we had n items, so in the third column, right?
Yeah.
N2, D2, we would acquire all the rest of the logs, right? If we had more items.
Yeah. So this is wrong, right? This should be reversed.
No, not that. The column.
Yeah. This one.
Yeah.
So yeah, I would get L1, L2, I would get L3, L4.
How is this?
But the thing is, I didn't wait till the end. I firstly didn't get the locks immediately at the beginning, and I'm not releasing locks in the end. I'm doing the minimal needed to prevent this.
So you acquire all the logs, right? At the first step.
Yes, I got all the locks.
So how is
But I didn't get this lock immediately. I didn't get L2 immediately. If this transaction had asked for lock for L2 for D2, it would have got it at this point. That's the difference. The reason why this is waiting is because the items are being accessed in the same order. That's a difference. Okay, that I waited till I needed it. And then at some point I know that I won't need more locks. Somehow I know that no if statements will be executed. Then by the way, in practice, we'll talk about this later when we talk about cascaded aborts, people often keep the locks till the end anyway. Okay? And the problem is this, that what if I got the lock, I wrote it, okay? This guy got the lock, this guy read it, okay? And later I say, I didn't like what I did, abort. This guy has read that value. What do I have to do? Abort him too. What if somebody's read his value? Cascaded aborts. Okay? So to prevent cascaded aborts, you do tend to keep your write locks till the end, which means that maybe there's read locks also. So we'll talk about that also. Yeah. So again, I have this mistake that's propagating, but you guys get the idea? That in this case, let's go and look at this case here. What happened? A non-two-phase different order, we got into this circular situation, right? Now under two-phase locking, this guy gets a lock, writes it, okay? Hasn't got locked to, which means this guy can get locked to. This guy tries to get locked to, it's going to wait. This guy writes to it's locked to, it tries to get lock one, it's going to wait, and this is your deadlock situation. Europeans call it deadly embrace. Okay, basically nobody's making any progress, and that's just fine. That's what we were designing for. Okay, the deadlocks and need deadlock detection schemes. Okay, so you guys believe, by the way, that it works. That if we have two-phase locking, we'll not have deadlocks. We'll either have deadlocks or they'll be serializable. You guys convinced? How would you prove it? So remember the transaction, let's talk in terms of transaction graphs. Okay, what cycles means. So T1 has an edge to T2. If T2 performs some operation before T1 performs an operation on that object, and those two operations are non-commuting, right? That's what these dependency things say. So non-serializable definition is there are cycles in the transaction graph. Okay. And we are claiming cycles in transaction graph under 2PL will lead to deadlocks. Okay, so how would you prove this? Just obviously, I'm going to do it in one slide, so it's not really a proof. Okay, but please use some intuition. So let's assume that there are cycles and there's no deadlock. Okay. What does that mean? That means T1 accessed D1 before T2 and T2, there exists some D1 in D2. That T1 accessed D1 before T2 and T2 accessed D2 before D1. Right? Under a two-phase locking, if a transaction accessed D1 and D2, it must have held both locks at one time. Right? Which means, and that must have either occurred before the other one or after the other one. Which means they couldn't have been a cycle. Okay. So, are you mathematicians happy with this proof? Okay. Ultimately, you understand proofs in terms of these high-level concepts. Okay, there's always this issue: who proves the proof? Because there can be bugs in the proof itself. But this is sort of the high-level argument for why this is going to work. Okay, and you understand 2P a little better. Questions? Okay. I forget where I'm going to from here. So we've changed our scheme here. Now this guy this guy reads, and then writes, this guy reads and then writes. Okay, at least I got these subscripts right, superscripts right. So what should we do? We should go and, since we have locking, okay, this guy before he does his read operation, he locks D1, right? Okay, he keeps the lock, and this guy goes and locks. Is going to lock, since he's also doing a read, he locks D1, okay, and he must wait till this guy frees it, and then he can read it, right? That's what our rules are saying. In this case, are these rules a little too strict? Could we have done better? Was this long wait really needed? There's really no dependency between from read to read, right? As long as we serialize him after, it's these operations that are causing this operation that's causing the problem. So my read had to unnecessarily wait. So the question is, should I have a single lock for read and write? Or maybe could I have different locks so that in this case I didn't have to wait? And just to show this more dramatically, T2's read is unnecessarily delayed. And look at this transaction case. Transaction 1 reads, transaction 2 also reads, transaction 1 writes, transaction 2 does nothing else. All it does is read, just a reading transaction. And yet under our semantics, there'll be a lock here. This guy will have to wait till he decides in his sweet time to go and release it, and then he gets to read. Okay. So should we then, that means, have different locks for different types of operations? Okay, and how do these locks then relate to each other? Okay, so let's go and have it. What this is implying is that we should really have a separate lock for read and write, right? So let's go and understand what the semantics of these locks might be. Okay, so now I'm not just requesting a lock, I'm requesting a read lock. Okay, I read. Okay, I request a read lock. And what does a read lock really mean? In this case, we don't want it to block, right? We can have multiple read locks in the same item. Okay, that's just fine. And he asks for a write lock. And what should happen? Sorry? Wait on the read lock. Okay, let him free it. Now you proceed. Okay. So concurrent reads allowed, concurrent read and write are not allowed. And concurrent writes are of course not allowed. Okay. So we have multiple lock types. So our semantics are, of course, if the item is unlocked and we want the read lock or write lock, we get the lock. Okay, so that's obvious. So if it's read locked and you ask for read lock, if it's write locked and you ask for read lock, okay, for the same reason, no. Okay. This is more compactly just represented as this way: shared lock and exclusive locks. Okay. Shared lock, yes. Shared, wherever there's an X, you say no. Okay? Okay, to make things even more fun, we have, so far we said O1, O2, okay, separate objects. What if we have a hierarchical structure? Okay, we have a session in which we have an application, in which we have some window, in which we have maybe a paragraph or drawing in which we might have a character or a shape, okay? And the question is, do you associate, where do you put locks here? You can talk about the granularity of locks, and they can be fine-grained locks or coarse-grained locks. You can just say, just lock the whole session, okay? Or you can say, let's go and lock each character. So what are the pros and cons for coarse-grained and fine-grained locks? Lock the whole session? What's the problem? No, so you can't have concurrency. Lock each character? Too hard? Hey, you're doing this course. Everything is, you want hard things, right? If it wasn't hard, every Joe Blow can build an app and make money, and what's the use of getting this education? Really? Now, if it's too expensive, it's too inefficient, that's an argument.
What do we gain from it? 'Cause yeah, it is
Concurrency.
more expensive.
Yeah.
We gain a lot of concurrency.
And
But we also get a lot of concurrency by just not using any locks.
but then you get a lack of consistency. Hey, it's all about having your cake and eating it too. Really, that's the thing. Where do we and it's not only is there space cost, but there's this time cost also, right? Every time you go and need to change a character, you have to get a lock for that character, right? And so there's a lot of messages being going to the central model.
And you're probably going to have to, if you're locking car by car, you're going to end up like having to do that deadlock avoidance thing.
A lot more times.
Like, all the time.
Yeah.
It's probably pretty expensive.
Yes, it is very expensive. Okay. Yes. Like I said, I never took a database course. Okay, I did take one database course, and I thought that was enough. But the second course was the one where they did concurrency control, and I really regret not doing it. But from what I remember and from what I've heard, I mean, these algorithms are pretty expensive. Okay. But the more concurrency you have, the more chance of deadlock there is. Okay. So again, I've given you two choices: fine-grained and coarse-grained. Is there some flexible choice in here that makes you pay the cost when you need it and not when you don't need it? That means I can lock, if I want to, at the character level, or I can lock at the paragraph level, or at multiple levels. Okay. So if I really need to lock the whole paragraph, why should I have to go and lock each character? That's silly. It's only when I don't know which characters I'm going to change. Let's say I'm correcting typos. Okay, and there's only 6 or 7 typos, and I just lock that little sentence or that little, and I don't lock the whole document so that you can be changing figures concurrently. And does that sound like a crazy idea that two of us editing a document, I'm fixing typos, you're moving figures around? Would you ever do it? The way I got into collaborative computing was when a student and I were trying to do that before the deadline. We needed to do that, and we didn't have an editor to do that. This was in the prehistoric times before Google Docs. So we essentially invented Google Docs and said that's what was the motivation for synchronous editing and how I got into it. Okay, so that's that. When you have deadlines, that's very, very useful. Okay. It helps to have papers follow West Coast deadlines, 12 p.m. West Coast time, and it's even best when it's Hawaii time. You get so much more. So every minute costs, is useful at the end. And deadlines. You guys, I give you 11:55 p.m. And okay, so we can have comparison and ideal granularity. Finer control means more concurrency, more lock-unlock operations, more chance for deadlocks, more locking overhead. Okay, and you can have variable grain. Okay, lock at the level you want to, and that increases the headache. Now, what does it mean to have variable grain locks? Okay, So fixed grain locking, I'm going to read item D1. So this is what's happening. The transaction 1 reads the whole D1. T2 only reads 1.A. Okay? Then 1 writes to 1.B, D1.B. Okay? And transaction, so what's going to happen with fixed grain locking? It's going to ask for a shared lock on D1, right? It's going to read the item. This is going to ask for since we have only one lock, we're going to ask for the whole item, right? It's going to be given that. It's going to read that item. And this is going to now ask for an exclusive lock and have to wait. This wait is totally unnecessary. It could have gone and just written B because the dependency is in this direction. There is no dependency here. This arrow shouldn't exist. Okay, there is no dependency, I'm sorry. Okay, and this dependency is artificial, the one that's imposed here. Okay. So T1 unnecessarily waits for T2 to finish right. What we want is variable grain blocking, where this guy asks for a shared lock on the whole item D1, reads it. This guy asks for a lock on 1.A, gets it. This guy asks for a lock on 1.B and gets it. Right? This guy frees it, and life is good. Okay, so this is variable grain locking working. You're afraid something might go wrong?
No, I mean, I guess it's just, I guess I'm not understanding how it's not just like, you just have an implicit, like, you're implicitly taking two locks when you take
The first lock.
one. Yeah, like so it's just like handy.
But I had to store the lock in only one place. This is one lock. That's like saying I implicitly take a lock for every character.
Yeah.
But that's not what really happens. You just have one lock stored, one lock to be processed, one lock to be looked up. Okay. It's more concurrency. So in this case, I looked at locks only at my level, right? Here, or did I have to go and consider locks at multi? Did I have to look at my parents' locks or my children's lock when I'm locking an item? Our reasoning happened to be that, oh, this guy's doing A, this guy's doing B, so they're fine. But could my parents' lock, could the ancestor lock prevent a descendant lock from? It should, right? And vice versa. So this guy writes on D1. He reads A. So this guy requests a lock for whole D1. Writes to D1. This guy requests for shared lock on 1.A, and should this shared lock be given? Okay. This guy frees it, and now he gets it. So you do have to look at your parents' ancestors' locks. Must consider lock at ancestor node. Search cost, how many ancestors can a node have? Depends on the height of the tree. Okay? And heights the number of nodes is large, but the height is small. Okay? So this situation is not so bad. What might be bad is if there's descendant independence. What if this guy got this lock first, and this guy does the write later? Okay, so he went and read 1.A. This guy wrote 1. So this guy went and got shared lock on A, 1.A, and this guy tries to get a exclusive lock on 1. Shouldn't be given, right? Because the descendant has that lock. So lock operation must consider lock at descendant nodes, and that's a much larger number of nodes to consider. Okay. So we run out of time, but the next thing to look at is how can we go and make the search cost lower. That we don't have to look at all the ancestors, which is not too bad. We should certainly not have to look at all the descendants when we're locking a node. Okay, and we'll come up with a totally different kind of scheme. We'll introduce more lock types essentially to solve the problem. Okay. So what I will do is I will go and put whatever I've done till today on the web. Okay, but I won't be creating the video. Okay, because the video I'll just do later. So we'll just see how this works later. What do we use? We use laser pointer, right? Okay. We were looking at transactions involving hierarchical objects. Okay. So here's transaction 1 that writes to D1. Here's transaction 2 that reads a particular component of D1, okay, A component. So T1 must go and get an exclusive lock. We saw there were write locks and read locks. Write locks were exclusive, read locks were shared. So it must get an exclusive lock on D1, and then it can write on D1, write to D1. And T2 must get a shared lock on 1.A. 1.A is a different item from 1. It is not locked, but since its parent is locked, transaction 2 should have to wait, okay, till the lock is freed. And so the lock operation at a particular node must consider lock at all ancestor nodes. Okay, we saw that. Okay, and there's a performance cost here, and the search cost is, and you guys all very quickly said yes. And the example is this, that let's say T2 got ahead of T1. It locked the A component, and T1 tries to write to it, wants to write to it, and T2 must get the shared lock, T1 must get the exclusive lock, and the exclusive lock should be given only if the T2 hasn't got the shared lock of the descendant. Okay, so the search cost here, the lock operation must consider lock at all descendant nodes, and now we're looking at a much larger number of nodes. Okay, so the question I asked at the end of the last class was, how can you make this perform better? Okay, and the hint is that here we assume, well, let me not give you a hint, you can ignore this hint. How can we make this faster? Okay, how can we make the cost constant? Or in the worst case, the height of the tree, okay, because you'll have to search the tree to find the node. So it'll be constant at a particular node, but to lock a particular node, starting with the root, it should be the height of the tree. Nick?
When a node acquires a lock, it could tell all of its parents or tell its immediate parent that it has acquired a lock, and that is done. And that is done when the lock is acquired, not when the second lock is requested. So when the second lock is requested, we just need to check, have any of our descendants told us that they've acquired a lock?
Okay, good, exactly. Okay, so what we want to do, and so then the idea is that when you lock a node, you tell all of its ancestors, not just the parent, right? It's locked, and if and so when another transaction comes in and tries to lock a bigger structure, it knows that some child is locked. Okay? So if I have a parent with elements A, B, C, and D, and A and B are locked, in the parent, what information would I keep? A is locked and B is locked? No, so there's some node N, which has children A, B, C, and D. Okay, A and B have been locked. What information do I exactly keep at node N? We know that A is locked and B is locked, C is not locked and D is not locked. And let's say this is shared lock. So what exact information should I keep at the parent?
That there is some child lock.
That there is some child lock? Is that, rather than keeping for all children, because then you would have so many locks. Okay? So we've got a time-space trade-off here. We're going to have more lock bits around in the tree, okay, so that we can save on time. But we're not going to have so many lock bits that the space gets high. Okay, so we want the smallest amount of information possible. Okay, so we're going to trade space for time. Here. So these are called intention locks. Okay, that's because when you're getting the lock, when you reach the, you don't have to go and tell the parent. You reach the child through parents. So as you're going along the path, you're leaving information there about what your intention is to do with the children. Okay, so that's why they're called intention locks. So the idea is that when you transaction 2 goes and says that, look, I'm going to lock ultimately 1.a. So what I'm going to say here is that I have an intention to lock some child of 1. Okay, that's an intention lock. And Joe, can we have the laptop down? Sure. And we go and then put a shared lock on 1.a. Okay. And now when this transaction tries to get an exclusive lock on node 1, it's denied. Okay. Because we know at this point some child is locked with the shared lock. You can't get an exclusive lock in the whole tree if some child is locked with the shared lock. Okay? So we'll have to come up with a lock compatibility matrix that involve not only S and X locks, but IS, IX, and another kind of lock. Okay? So then you go and read this node, and you free. You have to now, when you free both the lock and the intention locks. Okay? So intention lock is a flag in each ancestor of a lock node indicating the kind of lock. Okay, so it's kept at not only my parent, but my grandparent, and so forth till I go up. Okay. So how many of you guys have done compilers in some form? I guess I've asked this question before. No one, right? You have?
I took compilers.
That's why not. That's our grad students don't take compilers. Our compiler class is offered mainly at the undergrad level. Did you ever study attribute grammars? Okay. Do you remember synthesized and inherited attributes in attribute grammars? You've heard the term at least. Can you define synthesized and inherited attribute, or at least go and relate it to this stuff? So what does the word synthesized mean intuitively? It has to do with a tree. Sorry? There's a tree, there's an attributed tree. Okay? So when you talk of attribute grammars and compilation and interpretation, you're talking of the various nodes in a tree being decorated with attributes. Okay? They can be, for instance, if you have an expression that's a compound expression, then the child expressions have attributes that indicate, for instance, the value. If you're doing interpreter, you can do that. And then the parent expression's value is dependent on the child expression values, right? So that value attribute is synthesized up. The parent's attribute depends on the children's attributes. Okay? If you think of forget compiler tree, if you think of subclass and class inheritance of methods, a subclass inherits a method from the parent. So that's an inherited attribute. Okay, so you can have synthesized attributes where the parents' capabilities depend on the children's, or you can have vice versa. Okay, so when you talk of attribute grammars in compilers, if you've got a declaration in the top block and you've got a use later in the child block, then the use has to be checked against the parents, the ancestor's definition. Okay, you can't allow an int to be used as a double. Okay, so what you're seeing essentially is a synthesized attribute. Okay, you're seeing that the shared lock at the child creates a synthesized attribute at all the parents. Okay, it's dependent on that. Okay, you can evaluate it each time, or you can just go and store the value as a cache, and that's what we're doing here. Okay. So synthesized attribute is an attribute of a node that is a function of a descendant, and inherited attribute is an attribute that is a function of its ancestor.
So So like here in the PowerPoint, we have an intention shared lock on D1,
Mm-hmm.
and then when we free it to the intention ISF D1.A.
Oh, sorry.
Is that okay?
Sorry.
Yeah, I wasn't sure if that was like a copy paste thing,
Yeah,
or
yeah.
if like you're specifying. when
No,
you-
no. It's a copy paste thing. Thank you.
Okay.
So it's
In
just
that
D1,
case-
D1, and so you're locking down the tree and you're freeing up the tree.
Okay. So in that case, let's say that we have we want to lock 1.A.
Yeah.
So so T2 does the intention shared lock for D1, and then shared lock for D1.A.
Yeah.
Then another thread wants to lock 1.B.
Right.
Would it then like it? And I guess we're going to see the graph on the next page.
Yeah. So what's a lock compatibility matrix, right?
Yeah.
And what should happen? Let's reason it out. So it's going to put an intention lock on 1. Should that intention lock be allowed?
Yes.
Okay. Then it's trying to go and put an intention lock on 1.B. Should that be allowed?
Yes.
And what if the second transaction was trying to write to 1.B? It'll try to put a intention lock on 1, intention exclusive lock on 1. Should that be allowed?
Yes.
And then when it goes to B, so we'll see all the combinations.
But then if then one of those two threads releases its lock,
Right.
is that going to free the intention lock?
So very good. So what do you guys think? So in fact, what does this step really mean? Okay.
all of the carrots node, the child node, to release the intention lock.
Okay. So the intention lock should be released only when all the children have released them. Okay. That means this operation is really doing what? It's decrementing some reference count. Okay. Just imagine a count. Rather than keeping a track of A, B, C, and D, it just says, look, I have so many different shared locks in my tree, and every time you release it, the reference count decrements by 1. It's like garbage collection. Okay? And when it goes to 0, then the intention lock is actually released. Okay? So that's a very, very good point. Okay? I don't have actually this mentioned in my later slides, so that's something I won't have text here, but just do pay attention to the audio when you listen to it. Okay. Other questions? So, as Nick predicted, the next slide is giving us the compatibility matrix. So let's try to reason things out. So this means that some transaction has one of these locks on a node, and here we are talking about a transaction that wants one of these locks on the node. Okay. So given that some transaction has an IS lock and another transaction wants an IS lock, as we discussed in the previous slide. So okay, actually let's talk of all of the locks. I've gone and we talked of IS. I haven't really and I mentioned IX. Let's go and explain what each of these locks means. So IS means some descendant of the node will have a shared lock. Okay. IX means some descendant will have an exclusive lock. Anybody want to guess what SIX means? Shared intention exclusive. Well, so I'm giving you a hint. Why is it not ISX? Well, that's a hint. It's a shared intention exclusive lock. What should it mean? And put an and between those two things. It's a exclusive. Which means I lock that node as shared, and I'm then going to go and put an exclusive lock on some descendant of the node. Okay. So it's really trying to say that, look, I'm going to lock this whole tree, and that happens. You're going to read the whole document, and then you're going to change the abstract. Okay. So shared lock on this node and exclusive lock on some descendant. So it's like an inherited and a synthesized attribute. Okay? So when you put a shared lock on a node, essentially all the descendants get locked, right? So that's an inherited attribute. And when you and then the X part is synthesized. There's some node is going to be exclusive, so I put an attribute to this node saying that something is going to be exclusive. Okay, right. So now let's go and look at the lock compatibility matrix. So IS and IS, yes, IS and IX. We saw that in the previous slide.
So the one on top is the lock that's already there, and the one in the left column is what we're trying to acquire.
Yeah, and it's going to commute. You know, it won't matter which is the row, which is the column. But yes, exactly. So the row is what you have, and the column is what you want. So what you already have is an intention exclusive. Somebody wants to put an intention shared. Should they be allowed at that node? Yeah, we saw that last time. Okay, if they ultimately end up locking the same child, we'll detect it at that point. At this point, for all you know, that they are going to be locking different nodes. Okay, so this is yes. For the same reason, this is yes too. Okay, IS and S. Somebody's put a shared lock on the whole document, and I want to read a particular component of that. Okay, IS and SIX. Somebody's put a shared lock on the whole node. Some descendant has got an exclusive lock. I want to put a shared lock on some descendant, which may not be the descendant that the first node is going to lock. So, you guys are all saying, not. So, this commutes. So, the previous discussion, IS and S commute, and now we're going to put a yes here and a yes here. Right? IS and X. Can't keep saying, okay? So you're going to lock the whole tree, and somebody is locked the whole tree for writing, and you want to write some component of it. You shouldn't be allowed. So that's okay. IX and IX. You want to write some descendant. Somebody else has written a descendant. Okay, that's fine. IX and S. Somebody's put a shared lock on the whole thing. You want to put an exclusive lock on one of the children. No. Okay, because the shared lock was put on the whole tree, including the node you want to write. Okay, IX and SIX. Somebody shared reading the whole tree and writing some component of it. You want to write to some component of it. If it's the same component, at the component level, we'll have two X conflicts. But somebody's reading the whole tree, and you want to write to some component of the tree. Okay. Oh, I keep forgetting the commuting things. Okay, no. And IX and X. Somebody's writing the whole tree. You want to write to some component of the tree. Okay. S and S, of course. S and SIX. Somebody's no, right? Because you want to read something, you want to read that component that has got an exclusive lock. You want to read the whole tree. S and X, right? SIX and SIX. No, because both nodes want to read the full tree, and both transactions want to read the full tree, and each transaction wants to write to some component of the tree. So this is SIX and X, okay, and X and X. Okay, good. You like this matrix? So this whole matrix was invented by a guy called Jim Gray. Does the company Tandem still exist? Do you guys know? Have you heard of the company? Tandem was a fault-tolerant company on fault-tolerant computing. The idea was that two computers always work in tandem, one computer just behind the other. so that if one computer fails, the other one can take over. Just, you know it failed there, so it'll maybe do some other instruction after that. And Jim Gray used to work there. Unfortunately, he was in the news for other reasons also. He sailed off in San Francisco, and nobody found him after that. So there was a big hunt for his sailboat, and it's like the Korean Airlines plane. Nobody ever found the wreckage, and we were all the computer scientists who knew about him were, for weeks and months worrying about him, but it's left the news. If you probably Google, you'll find something about it. Okay. Could I have done these two? So I think that's what I pose. Could I have asked for the shared lock first and then the intention lock later? I asked for the intention. In this case, I asked for the intention first, then I went to the shared lock. And that makes sense, right? Because I'm going down the tree. But say I really did the other way around. I went to the node I want to lock, saw that I can get it, and then went out later to go and advertise that to my parents that I have the lock.
I think we might have to do it the other way around, because if we do the intended shared lock first, then someone else, some other thread has an intend exclusive lock before we're able to do our regular shared lock. Wait.
So are they going to be able to put that lock? We've already put the intention shared lock on the parent. So they come in and try to put the IX. Okay, yeah, they'll be able to put the IX lock. That's fine. It's the IX lock you're saying, not the X lock, right? Transaction 2 does the X lock or the IX lock?
Transaction 2 does the. How about they do the SIX lock? Let's make things fun.
Okay. So you put the IS lock, and they want to put the SIX lock. Do you think they'll be allowed?
Yeah, they're allowed to do that.
Are they? Okay, yeah, fine. Because we are putting the intention shared. Yeah, cool,
Yes.
cool, okay.
And so then the first transaction, the original transaction, tries to get the S lock.
Right.
And the S lock is on a different node than the past ones we're talking about, so there's not a problem there.
Yeah, it's not a problem there.
Okay.
You have to have all the locks, before you can do something. If you don't go all the locks, you'll wait. Okay. So the question is, should this transaction put it on the children first and then the parent, or the vice versa? And from performance point of view, why are you going back up the tree? I mean, it's all constant time, but why are you doing that? So can you guys think of a reason why, besides that, to not reorder it? So I put this lock first. Then I go up to the parent. Could something have happened between the time I put this lock and I go to the parent? Somebody else has put the lock there, okay? And now I have to wait, okay? And you can get into a deadlock situation where basically, because everybody's not accessing locks in the same order, okay, the chances of deadlock are less when locks are requested in the same order, okay? When they're accessed in different orders, then deadlock chances increase. So what happened here was that this guy came first, and he had to wait. That's just bad. Okay, and then you can also get into deadlock situations, perhaps. Okay, so it just makes intuitive sense to lock, along the path. You'll find the child from the root. Okay, so unless you've got some kind of hashing function that goes to the child directly, but in this case, you assume that you go down the tree. So you put locks in this order. Questions? Okay, so we've taken hierarchical objects which exist in the real world, and we found a way to lock them efficiently. let's go back to this example of the system sync that I showed you earlier, where you edit, which is asynchronous system. Okay, so I can be interacting, you can be interacting, and then we can sync later. Okay, so so what happened here was that the ticket price was 23.5.